Hi all, welcome back to the discussion on quantum optics. In the last lecture, we have actually just introduced what is quantum optics, what is the boundary between the quantum optics and classical optics. So in this lecture, I am going to formally introduce what is quantum optics by quantizing the electromagnetic field, or more particularly the quantization of single mode field. Okay, so we know that if you consider an electromagnetic field which is confined in a cavity, obviously it has to satisfy the Maxwell's equation, or you can write it. It has to satisfy the wave equation, because the wave equation is simply derived from uh, the Maxwell's equations in vacuum. So these are the wave equation: del square E equal to 1 by c square dot square A by dot A square, and del square B equal to 1 by c square dot square B by dot A square. So these two equations are the wave equations of electromagnetic field inside the vacuum. Okay, so then the total Hamiltonian I can write as it is half epsilon 0 E square d tau plus 1 by 2 mu 0 B square d tau. So if you just integrate the energy density of electric field and magnetic field, you will get the total Hamiltonian, and it is represented by equation number 3. Now, in order to make it simple, we are going to consider a single mode for the electromagnetic wave. So, what is by single mode? The single mode is the field with fixed frequency and fixed polarization, and as well as fixed direction. So, if an electromagnetic wave satisfies these conditions, then I can say that it is of single mode. Suppose if different directions are present in the cavity, or different frequencies or different polarizations are present, then the field is no longer single mode. So such fields are called multi-mode field. Okay, so the field usually called multi-mode if there are multiple frequency or multiple polarization. So if any of this condition violates, then it is called multimode. Okay, so that you can keep in your mind. Okay, now in this section I am going to discuss only about single mode field. Okay, now again, in order to make it simple, so consider the electromagnetic wave is confined along z direction, that is the cavity is along one direction. Okay, so if the cavity is in one direction, I can represent the electric field which oscillates along x, and magnetic field along y, and direction of propagation is along z. And we can write E is exi, and B is equal to b by j. And it is possible to find this expression for Ex and By. Okay, now we can find the total energy by integrating the energy densities. Now, what will be the expression for Ex and By? So, the expression for Ex and By we have briefly discussed in the last lecture. So, if you just go through it, I have already found the expression for Ex and By, and the same thing I have used here. So this Ex of Zt I can write to omega square by epsilon 0 V all raised to half Q of t sine of kz, and similarly By is this. So not that this is an electromagnetic wave confined within the cavity, so it has to satisfy the boundary conditions. So these two, electric field and magnetic field, will satisfy the boundary conditions, and I can write these as equation number 4 and equation number 5. Now, if you integrate this, both electric field and magnetic field, I will get the total energy, and total energy I can write half q dot square omega square q square. Okay, so this equation is similar to the Hamiltonian of harmonic oscillator in classical as well as in quantum mechanical. The harmonic oscillator Hamiltonian can be written like this. So we have a similar structure, but there is a slight variation. Fundamentally, there is some difference. If you compare this to expression, there is no mass in equation number 6. Okay, because this is the electromagnetic field, so no mass component is present, but still the mathematical structure is almost same. So in order to make this comparison easy, I am going to denote my p q dot sp. So therefore, the total Hamiltonian of the electromagnetic field which is confined in this one-dimensional cavity, I am writing as half p square omega square q square, and it can be my equation number 7. Okay, now if you get this kind of Hamiltonian, it is also possible to change this Hamiltonian in terms of operators. So this kind of thing we have already studied in quantum mechanics of harmonic oscillators. So the same steps I am going to follow here. So in order to quantize this system, we are going to introduce the quantization postulate, which is the Q, the commutator between the Q and P. I'm going to denote as IH cross. So this is called, basically called the quantization postulate. Okay, so from here onwards the quantization comes. Okay, now in order to rewrite this Hamiltonian in terms of the operators A and A dagger, I am going to introduce the A and A dagger operators of this form. A is 1 by 2h cross omega, omega q plus ip. So these steps are very similar to the steps we have done in for to find the expression for Hamiltonian of quantum harmonic oscillator. Only difference is here there is no m. Okay, but all other steps are almost the same. So once you reach the equation number 7, so after that it is the steps are almost same as the steps that you are involved in, involved in the derivation of quantum harmonic oscillator. So this can be equation number 8 and equation number 9. So these are the two operators. I don't know what is the meaning of these two operators, so I just introduced two operators, A and A dagger. Now the important is, if you introduce these two operators, it is possible to express the Hamiltonian is of the form A dagger A plus half h cross omega. So this I have skipped few steps here, so you can do it very well because you have already done the derivation of harmonic oscillator. So just go through it and just then you can do it all these steps your own. So there is no need of help required on this. Okay, so this A dagger A hereafter is called number operator. So we'll quickly see why it is called number operator. You might be knowing the reason. So anyhow, I will explain it. Okay, so in order to find the meaning of A dagger A, have to do some algebra. So first of all, I am going to do the commutator between A and A dagger. I already know the expression for A and I know the expression for A dagger. I know the commutation between Q and P. So if we just use the commutation rule, I can show that the commutator between A and A dagger is simply 1. Okay. Then what I have done is I can express my Q and I can also express my P. These are the operators we have already know. So let this is equation number 10. So this can be equation number 11 and Q is equation number 12 and P is equation number 30. Okay, so once you express this Q and P in terms of A and A dagger, it is possible to express the electric field and magnetic field operators. So the electric field now I can write as epsilon 0 sine of kz A plus A dagger. So this can be equation number 14. And the magnetic field I can write as B0 cos kz A minus A dagger. So there are certain constants. So if you look at, this is not epsilon 0, this is E0 and this is your B0. Okay, so that's all about the quantization of electromagnetic field in the cavity. Now we are going to use this information to represent the Hamiltonian and as well as to get the meaning of the operators A and A dagger. So if you summarize it, in case of a single mode field, the Hamiltonian is very simple. The Hamiltonian of the single mode field, I can simply write A dagger A plus half h cross omega. What the physical meaning of it, we will discuss it. Okay, and the correspondingly the electric field and magnetic field, that can also be represented in terms of this A and A dagger. The electric field is connected with A plus A dagger and magnetic field is connected with A minus A dagger. Okay, so that's all for now. And next what we are going to discuss is what is the meaning of this A and A dagger. So from that you will come to know what is the meaning of H, and as well as you can define the different the various states for the field inside the cavity, and as well as you can also find the variation of this field on different possible states. Okay, so next we can discuss introduce a new state called the Fock state. The Fock state is also called the number state. So the Fock state or number state, you might be familiar in quantum harmonic oscillator system. It is the eigenstate of a dagger A operator. Okay, and it is usually denoted by symbol ket n. So the ket n is the representation for Fock state, and this is the number state of, so this is an eigenstate of a dagger A operator. So what is the meaning of it? That is, if you act a dagger A on the state n, you will get the same n. Okay, there is no change in state, but you will have some scaling factor, so you will get some number here, some complex number in general. Okay, so if a dagger A is Hermitian, this complex number must be this number must be real, but in general it may be a complex number. Okay, so it must be some number. So this is what is the meaning of the eigenstate and the eigenvalue. So this ket n is called the eigenstate of a dagger A operator or eigenvector of a dagger A operator, and this number is called the eigenvalue, and in general it can be a complex number. Okay, so then if you just apply this into our equation number 10, if you just apply this into equation number 10, okay, so the H acting on this ket n would be a dagger A plus half H cross omega acting on ket n, or H acting on ket n will give n plus half H cross omega. So what I am getting is H acting on ket n is n plus half H cross omega acting on ket n. So what is the meaning of this? So this shows that your ket n or your Fock state is also an eigenstate of the Hamiltonian, because once you act the Hamiltonian on ket n, the ket n remains the same. The state, there is no change in the state. Okay, and what is the final result? The result is the state become some factor multiplied by the state, and this factor, this n plus half H cross omega, I can call it is the eigenvalue, or more correctly it is the energy eigenvalue. So this shows the ket n is also an eigenstate of the Hamiltonian with eigenvalue n plus half H cross omega, or we can also call it is the energy eigenvalue, because since it is the eigenvalue of the Hamiltonian operator which is corresponding to energy. Okay, so that is the physical meaning of the state n. Okay, so state n will contain n plus half H cross omega of energy. Okay, next we can just go ahead to get the meaning of the operator A. So for that, what you can do is just act a dagger A operator on a dagger ket n. So ket n is a vector, and the ket n is acted by some a dagger operator. After that, I am going to act a dagger A operator. Okay, so I am just doing a simple algebra, and this algebra may be familiar to you earlier as well. Okay, so what I can do is I can show that this would be exactly equal to n plus 1 a dagger ket n. So there's some algebra I've used, and for this algebra I've used basically the commutator, this information commutator a dagger is 1. So using this information I can show the steps. Okay, I'm not going through each steps step by step. You can just go through it. I think that you can do your own, or just pause this video and do this exercise and just ensure the final result is exactly n plus 1 a dagger n. Okay, so that I am leaving to you. I am not going to explain each of the steps. Okay, but now what is the final result? The final result is the a dagger ket n is on the left side and a dagger ket n is on the right side. So the vector a dagger ket n is not changing by the action of a dagger A operator. So that means a dagger ket n is also an eigenstate of a dagger A operator. Okay, remember a dagger ket n is also an eigenstate of a dagger A operator, but correspondingly the eigenvalue is n plus 1. Okay, now if you look at this, a dagger A acting on ket n gives n ket n, and a dagger a acting on a dagger ket n gives n plus 1 times a dagger ket n. So what is the physical meaning of this? Okay, so this shows that the a dagger ket n is also an eigenstate of the number operator a dagger a, but with the corresponding eigenvalue n plus 1. That means the action of a dagger on n must be increasing the eigenvalue of ket n by 1. Okay, so a dagger acting on ket n is eigenstate of number operator with eigenvalue n plus 1, means the a dagger acting on n must be increasing the value of ket n, the vector ket n to vector ket n plus 1, because if you have a dagger a acting on n plus 1, what would you get? It would be n plus 1 acting times n plus 1. So that means your a dagger acting on n must be a new vector, and it must have the value n plus 1. So the a dagger is increasing the eigenvalue of the vector by 1. So more correctly, a dagger acting on n, I can write some coefficient into n plus 1. So in the same way, I can show that a acting on ket n must be decreasing the eigenvalue by 1, or a acting on n would give n minus 1, and I have introduced some the coefficient, constant coefficient dn on the left side. Okay, so now I have got what is the action of, or what is the physical meaning of this a and a dagger. A dagger increases the eigenvalue of the Fock state by 1, and a decreases the eigenvalue of Fock state by 1. So therefore, hereafter I can call the a dagger as the creation operator and a as annihilation operator. Okay, now you can find what is the expression, would be the expression for the Cn and Dn if you want. So for I have just shown how to find the expression for Dn. So for that we have calculated the expectation value of a dagger a on the number state. So this can be written as, so a acting on n would be Dn n minus 1. So its complex conjugate a dagger acting on bra n would be Dn complex conjugate n minus 1. So this Dn and Dn star must be some complex number. It can be taken outside, so it become mod Dn square here, and it would be the inner product n minus 1 n minus 1. Here it is the inner product between the n and nn. Okay, so finally I can show that this Dn is simply square root of n, or a acting on n I can write root n times n minus 1. So in the same way I can show that a dagger on ket n would be root n plus 1 times n plus 1. So this you can do it your own. Okay, I think all these steps we have done in the quantum treatment of harmonic oscillator. The same steps follows here. So only the difference is it is at the starting point. There is the expression for Hamilton is slightly different, because when you come to the quantum optics, there is no mass involved, because we are treating about the electromagnetic field. So there is no mass involved, and the definition of Q and P are slightly different. In quantum harmonic oscillator, the Q and P, Q is corresponding to position, P is corresponding to momentum. Here it is not exactly the position and momentum. It is the characteristics of the field, not the particle. Okay, so now if you look at the Hamiltonian, the Hamiltonian is of the form Hamiltonian acting on n is n plus half h cross omega n. Okay, now this ket n is a Fock state. Okay, so the ket n is corresponding to the energy of n plus half h cross omega, and if you act the annihilation operator, the a operator on the number state, it decreases the quantum number by 1. Okay, so on the continuous action of this annihilation operator, this the value, the energy value would continuously it can decrease. Okay, so if it is keep on lowering the eigenvalue, the eigenvalue may go to the negative infinity, and that is practically unphysical. Okay, so if you look at the energy level diagram, so if you have some energy n plus half h cross omega, then further the action of A decreases the energy eigenvalue by n minus 1, n minus 2. It cannot go to minus infinity. Why this cannot go to minus infinity? The reason is if it can come to minus infinity, obviously all the system will have the tendency to occupy the lower energy level. So if the lower energy level is at minus infinity, then you can get infinite amount of energy by de-excitation of field from an excited level. So if a field is de-exciting from get n to minus infinity, the amount of energy you are going to get out is infinity. So that is not possible, because we are always getting a finite energy in all kinds of transition. So the infinity energy, the infinite lower energy is not possible. So that means there must be some lower bound for the energy, and the lower bound for the energy, the corresponding state I am going to denote as ket 0. Okay, so the ket 0 is the lowest possible state. It cannot go further down. Okay, so that means how we can set this lowermost possible energy state by introducing the annihilation operator. So once the state reaches ket 0, then the further annihilation is not possible, further lowering is not possible. So that means the A acting on ket 0 must vanish the system. So A acting on ket 0 must become 0. Then what would be the A dagger acting on ket 0? Okay, A dagger acting on ket 0 increases the energy, okay, and the state become ket 1. A dagger acting on ket 1 become ket 2, and A dagger acting on ket 2 become ket 3, and so on. So that is basically the excitation, because and excitation is possible. Okay, the excitation can go up to the infinite level also, because by supplying infinite amount of energy, it will not go spontaneously to the infinite amount of energy. We have to supply the energy, and in principle there need not be any upper limit for the energy, but the lower limit, there must be some finite limit for the lowering of energy, because if there is no finite limit for the lowering of energy, then the de-excitation may give the infinite energy, and that is not physically happening. So obviously there must be some lower limit, and the lower limit I put as ket 0. Okay, so with this what happens is the energy level I can denote like this. So we have some ket 0 state, and ket 1 state, ket 2 state, and so on. It can go up to infinity, there is no issue. And ket 0 state will have energy half h cross omega, and ket 1 will have energy 3 by 2 h cross omega, because ket n has energy n plus half h cross omega. So this become 5 by 2 h cross omega. So ket 0 to ket 1 would be possible by action of a dagger, and ket 1 to ket 2 would be possible by action of a dagger, and so on. Ket 2 to ket 3 is possible by action of a dagger. So the action of a dagger increases the energy by the amount of 3 by 2 h cross omega, and it increases the quantum number by 1. Okay, so here the possible energy states I am going to denote ket 0, ket 1, ket 2, etc., corresponding to n0, 1, 2, 3, and the energies are half h cross omega, 3 by 2 h cross omega, 5 by 2 h cross omega, and so on. And in general, it is possible to represent your state, the ket n state is of this form. So this you can do as an exercise. Just try to find it, because what I have done, I have just showed the few steps how to write ket 1, ket 2, ket 3. So do it a few more steps, and you can generalize it. Okay, now if you look at ket 3, the ket 3 is 1 by square root of 3 a dagger acting on ket 2. And what is ket 2? Your ket 2 is a dagger acting on 1 divided by root 2. So this become 1 by square root of 3 into 2 a dagger square acting on ket 1. So you can generalize this. So this is ket 3. Now you can write ket 4 and you can generalize what is your ket n. So ket n I can write 1 by square root of n factorial a dagger raised to n ket 0. Okay, so we can say that this ket n has n photons because it has energy n plus half n cross omega, and the number of photons is the number of excitation of field from the ground state. Okay, so in quantum optics, in the quantum optical point of view, the ket n is called a quantum state with n photons. So that means what is meant by ket 0? So ket 0 is quantum state with 0 photons, there is no photon present. And ket 1 is corresponding to 1 photon. Okay, so the ket 0 to ket 1, it is basically the system excited once. So the once the system excited once, we have 1 photon. If the system excited twice, we have 2 photons. So here we have 1 photon here, and we have 2 photon here, and we have 3 photon here, and so on. So basically the number of photon is the number of excitation of the field from the ground state. Okay, so in the quantum optical language, in the language of quantum optics, the number of photons is number of excitation of fields from ground state. Okay, so how many times it is excited from the ground state, that gives the number of photons. So there is the basic idea about the photon in quantum optics, and you can see the similar kind of concepts when you're going to the quantum field theories as well. In quantum field theory, the particles are treated to be the excitation of field modes. So here also the same thing, the photon is treated as the excitation of field modes. Okay, now that is about the single mode field, and if you are going to the multi-mode field, what happens is the total Hamiltonian, I have to write the sum of Hamiltonian of each mode. Okay, so we have to introduce the number operator, the annihilation creation operator for each mode. So for one mode I can denote by symbol A1 and A1 dagger, and second mode I can write A2 and A2 dagger, and so on. So therefore the total Hamiltonian would be A1 dagger A1 plus half h cross omega 1, and A2 dagger A2 plus half h cross omega 2 plus etc. So that means here A dagger A1, this is the number operator corresponding to the first mode, and we have to define Fock state corresponding to each mode. So the ket 1 is a Fock state of first mode, and ket n2 is a Fock state for the second mode, and so on. Okay, so in general the ket n, a general state, I can write as the tensor product of all possible state, the ket n1 tensor product ket n2 tensor product ket n3 etc. Or you can we simply write as ket n1 n2 n3 etc. So this is the representation for a multi-mode field, and probably sometimes you may have to discuss a two-mode field. So consider a field with the two different polarizations. So these two different polarization has to be treated as two different modes. So in that the state, if the state is only a two mode, then I have to write ket n as n1 n2. Okay, so suppose if you have a two mode, the ket n, I can write n1 n2. So what would be the A1 annihilation operator for the first mode A1 acting on ket n? This is simply A1 acting on n1 comma n2. This A1 will act only on n1, not on n2. So therefore this would give root n1. This A1 will decrease the number value of n1 by 1, and the value of n2 remains same. And similarly, what is the action of A2 on this ket n? It would be square root of n2 n1 n2 minus 1. Okay, so this is the just the introduction of the formal introduction to the topic of the quantum optics. We have introduced two things. So first of all, we have expressed the Hamiltonian in terms of two new operators, A and A dagger, or A dagger A, which is called the number operator. And we have found what is the meaning of this A and A dagger completely. And we also introduced what is called a Fock state. Okay, so the Hamiltonian, I can write the Hamiltonian of a single mode field, I can write A dagger A plus half h cross omega, and the electric field and magnetic field in terms of A and A dagger A can be written of equation number 14 and 15. And we have discussed one particular state. Remember, the Fock state is only a one possible state. There are many possible states available for uh, a quantum system. So this is a simplest possible state. It is also called the energy eigenstate or the number state. Okay, so this the number state or Fock state is called it is the eigenstate of A dagger A, and the action of A and A dagger on this eigenstate is the A dagger increases the eigenvalue of the Fock state by n plus 1, and A decreases the eigenvalue by n minus 1. Or if you look at in terms of the Hamiltonian, the A dagger and A increases and decreases the energy eigenvalue, and there must be some a lower bound for the possible energy eigenstate of this optical system, the quantum optic system. And the lower bound I have denoted by symbol Ket0. So Ket0 is my ground state, and the possible excitation states are the Ket1, Ket2, Ket3, etc. These are the possible state. And in this excitation, by the action of A dagger, then the number of energy, the amount of energy is increased by h cross omega. So in each of these excitation, the energy increased by h cross omega. So that is why the number of excitation is corresponding to the number of photon in the field mode. Okay, so that's all for now, and we also discussed how to represent a multimode field. So in the next class, we are going to discuss what is the energy fluctuation of electromagnetic field, or what is the fluctuation, particularly the fluctuation of the electric field of single mode field. Okay, so that we can see in the next class. So see you soon. Bye.